A couple more problems on stoichiometry. So the first one is quicklime, which is calcium oxide, can be produced by heating limestone calcium carbonate. How many liters of carbon dioxide gas, so this is the gas, how many liters of carbon dioxide gas are produced at 825 degrees Celsius and 754 torr from 45.8 kilograms of calcium carbonate. So a very traditional type of stoichiometric problem, except that we have to give our answer in liters and not in grams. Okay, so the first thing we have to do is find moles, do the mole ratio, and then convert that into liters. Okay, so that's our strategy. And in the meantime, we also have to convert all the units, okay, and all the wonderful things. So in any case, let's get started first with finding the moles. So we start with 45.8 kilograms of calcium carbonate, which first we convert to grams, so 1000 grams in 1 kilogram, and then we convert that into mole. So in 1 mole of calcium carbonate, we have about 100 grams of calcium carbonate. Again, this is coming from the periodic table. And then finally the mole ratio, which the equation is nicely balanced. So we have 1 mole of carbon dioxide in every mole for every mole of calcium carbonate. Okay, so kilogram, grams, and then moles calcium carbonate. We are left with moles of carbon dioxide, which is about 458 moles. Okay, so now that we have the moles of carbon dioxide, we are going to go ahead and find the volume using PV is equal to nRT, and again it's going to be volume, so volume is equal to nRT over P. Okay, so we need some information before that. We have the moles, we have the R, and temperature is 825 plus 273, which is 1098 Kelvin, and then the pressure that we need is 754 torr. So let's convert that into atmosphere, 760 torr, and this is equal to 0.9921 atmosphere. Okay, so we need these two in order to work with our equation. So then 458 moles times 0.0821 liters atmosphere mole Kelvin. Temperature is 1098 Kelvin, and the pressure is 0.9921 atmosphere. Okay, again cross out the units. Mole, we're left with liters, and this is equal to 41615.5 liters, which then is equivalent to 4.16 times 10 to the power of 4 liters. Okay, so very simple, straightforward stoichiometry. Now I'm going to take another different kind of problem, okay, which is all dealing with volumes. Okay, in here, everything is in gas phase also. In the previous problem, we had some which were solid and then some which were in gas phase. But let's read this problem first. How many liters of oxygen? Are consumed for every 10 liters of carbon dioxide produced? Okay, so carbon dioxide is 10 liters, okay, of carbon dioxide produced in the combustion of liquid pentane, which is C5H12, and combustion, remember, is reaction with oxygen. So the equation is given to us, and pentane is C5H12, which is burning in oxygen, that's combustion, giving us carbon dioxide in gas phase and water in liquid phase. Okay, so this is a little bit different kind of problems because we are now working with gases, okay, all the way through. So the first thing we have to do for any stoichiometric problem is go ahead and balance the equation. So here we have 5 carbons, so we go ahead and put 5 here, balance out the equation, and 6 hydrogen, and then 8 oxygen. Okay, so then our question is, how many liters of oxygen are produced from 10 liters of carbon dioxide? And since this is at STP, molar volumes are the same. Okay, so molar volumes, remember, are 22.4 liters. Okay, and once we know the moles of each of the gases, then all we need to do is interconvert them. Okay, we don't need to worry about PV is equal to nRT. We will not use that, okay, in this equation. So we just need to focus more on the mole ratios, which means that if we have 8 moles of oxygen, all right, this is equivalent to 8 liters of oxygen, okay, in a way. So there's the direct conversion there, and so we'll use the mole ratios, okay, to figure out how many liters of oxygen are being produced or are being consumed by 10 liters of carbon dioxide. Okay, so of course the most simple thing you can do is you can look at the mole ratio of these two. So this is twice 10 liters is twice that of 5. So oxygen, which is 8, which has an 8 coefficient, it should be also twice then, okay, of that coefficient. But we'll go ahead and set this up so you kind of understand this, but otherwise you if you got where I'm getting with the 5 and 10 ratio, the 1:2, then you already know the answer. Okay, otherwise let's work with liters of oxygen, and that is set up as, so we have 10.0 liters of carbon dioxide. Okay, and for 10 liters of carbon dioxide, if we say that for 5 liters of carbon dioxide we always get 8 liters of oxygen, and that liters is coming from this mole ratio, okay, over here, because we can convert the moles, these coefficient, these moles, directly into liters. Okay, and so then 10 divided by 5 is 2, and then times 8 is 16, okay, liters of carbon dioxide. So at STP the calculations are slightly easier, okay, in fact they're actually quite easier, okay, to do. So keep that ratio in mind then, okay, because that's all you need to work on. You don't need the PV is equal to nRT when you're working with all gases and you're working at STP.